So consider this co-chain complex. So this co-chain complex is M. So this is a co-chain complex. These indices are increasing from n minus 2, we go to n minus 1 to mn, and then you have these differential maps. So again, the kernel of the map or the arrow going out of mn minus 1, this contains the image of the map coming in. So this is the condition for co-chain complex. Now recall the definition of cohomology. So say we want to compute the cohomology group Hn minus 1 for this chain complex. So that is, we want to compute the cohomology group here. So you take the kernel of the arrow going out, dn minus 1, over image of arrow coming in, which is dn minus 2. So kernel we always write as zeros n minus 1. So this is just the definition. And image of dn minus 2 is nothing but this dn minus 2 applied to m's n minus 2. So instead of dn minus 2, we will always write d, because it will be clear from the context which d we are talking about. So this, now copy the numerator as such. For the denominator, notice that we have put this additional term dmn minus 3. So that is because mn minus 3 is right here. So you take an element x here, it gets maps to dx here, and since the image here lies in the kernel of the next map, so when you apply this map d to this, this becomes 0 here. So this is anyway 0 once you apply d to it. So we can incorporate this image of this module mn minus 3 here, because this will become 0 here. As you can see, x becomes dx, and then this becomes d2x, which is 0. So we are writing in this form because we need this form. So let us now define a map D which goes from mn minus 2 over this to zn minus 1. So this is the denominator, this is the numerator. So this is nothing but the co-kernel of the map. So this is co-kernel of our map here. So you define hn minus 1 as co-kernel of our map D. So this we need. So the second thing we want to find out is what is the kernel of the map. So we want to answer this question, what is the kernel of the map? So first let us compute the cohomology group at this n minus 2. So n minus 2 is right here. So again you have kernel of the arrow going out over image of the arrow coming in. So kernel of dn minus 2, image of dn minus 3. So because coming in is dn minus 3. So this dn minus 2 you just write as d, but this is d of mn minus 2. And you modulo out d of mn minus 3. So this you write as kernel of d mn minus 2 over d mn minus 3. So nothing much has changed. In this case you first take the kernel and then modulo out with the image. Here you first modulo out with the image and then take the kernel. It is not going to matter in any case because this d square would be 0. So this makes sense. So the kernel of d, so kernel of this map, now you can see kernel of this map, the d is acting on this, so kernel of this map is hn minus 2. So kernel of d is hn minus 2. Co-kernel was this and kernel is this. So this came from our chain complex M. So now consider short exact sequence of chain complexes. So you have M, and then you have L, and then you have N and 0. So this is short exact sequence of co-chain complexes, because we have a co-chain complex here. We are talking about cohomology groups. So corresponding to M, we have this, which we have just shown here. Corresponding to L, we have this. Corresponding to N, we have this. So we have, just like we constructed this thing from this co-chain complex, you can construct this and you can construct this. What we have not shown is the exactness of the green arrows. So we still have to show that the green arrows are exact. So we have to show exactness of green arrows. So this we will show later. So for the moment you assume that this is true. So if this is true, now you can use the snake lemma. Then you have kernel of this dm, kernel of dl, kernel of dn, co-kernel of dm, co-kernel of dl, co-kernel of dn. So just the snake lemma. But now you know this kernel of dm here, kernel is right here, hn minus 2. Kernel we said is hn minus 2. So this is hn minus 2 of m. Co-kernel is hn minus 1. So this is hn minus 1 of m. So this again, this is for co-chain complex L. So you have hn minus 2 L, hn minus 1 L. And here you have hn minus 2 n, hn minus 1 n again. So notice how we are going from n minus 2 to n minus 1. So we are increasing the index here in the case of cohomology or co-chain complexes. So now we have to just show the exactness of green arrows. So notice that this is how the short exact sequence of co-chain complexes will look like. So in the proof of snake lemma, we showed that if you're given a diagram like this, then you can form an exact sequence like this. So exactly as in proof of snake lemma. So in the proof of snake lemma, we showed this, that you're given a diagram like this, this will be exact. So this is kernel of this map dn minus 1, this is kernel of this map, this is kernel of this map. What is this? By definition, we write it as zeros of n minus 1 of our co-chain M. This by definition we write as zeros, but they occur at so this n minus 1 is n minus 1, this chain is L. So this is again zeros, but our chain is n. So this kernel is nothing but the zeros. So instead of kernel we are writing zeros. So this exactness follows from the proof of the snake lemma. That is, in the proof of snake lemma we showed that this is exact. So this you copy right here. So this part is exact. So now we want to prove the exactness of this part. So again, in the proof of snake lemma we showed that this this is the co-kernel. So this is co-kernel of dm. So this is co-kernel of dm. This is co-kernel of this map, and this again is co-kernel of this map, just by definition. So in the proof of snake lemma we showed that, you know, if you have complexes like this and you have maps like this, then this is exact. So this was in the proof of snake lemma. So now this is precisely this, as you can see. So this exactness carries over here. So this is exact. So therefore we can use snake lemma and get the conclusion we wanted to.